What is the Hall effect? The Hall effect is the most commonly used method for measuring magnetic fields. This is a thin conductive plate. Taking a copper plate as an example, we apply voltage across the two ends of the copper plate, allowing current to flow through it, and electrons will flow from one side of the plate to the other along the wire, at this time, near the plate. Introducing a magnetic field, the motion of electrons will be disturbed due to the Lorentz force. In this case, electrons will deflect to one side of the plate, while positive holes will deflect to the other side. By connecting a multimeter, we can measure the voltage, thus obtaining an effect that produces measurable voltage. This is the Hall effect.
We'll be discussing a misconception which we all have, is that the electrons and holes moves in opposite direction in Hall effect. This is a common misconception and everyone have. The real truth is that they both move in same direction. So this is something which is I am saying, but most of you may not agree with this. But like I will show you the proof why or how we can say this. So let's just start with a simple case. Okay, suppose there is a rod. This is a rod hinged at this point, and this dot represents the uniform magnetic field, which is upward. Magnetic field is upward above the plane. Velocity is in this direction. So if you v cross b, you get a force in this direction. Okay, velocity is in this direction, magnetic field is in upward, you have v cross b, and the force is in this direction. Okay, for positive charge. So okay, so for right now you know what's the setup. Okay, so and like assume this rod is a intrinsic semiconductor, so it has holes and electrons both. Okay, but it is hinged at here, so it is this rod is rotating like this. Okay, so the direction of velocity vector is same for both holes and electrons. See, this semiconductor will have holes and electrons, you know this. And since the rod is rotating like this, so every hole or electron, both are having the velocity in this direction. Okay, in same direction, it's along phi cap, to be more precise. Both of them are having along phi cap their velocity. So if you see the formula of Lorentz force, it is force is equals to q v cross b, charge velocity times magnetic field. So if we do the calculation for holes, we get the force to be upward. The force is this for holes, and the force is negative for electrons. Why? Because the q value is minus e for electrons and plus e for holes. So currently, are you with me? Do you agree with this? That yes, the electrons and holes will move in opposite direction. Is it okay? Yes, it's completely agree with the principles of Lorentz force. So at here what we can see is that when both type of charge carriers are having velocity in same direction, the Lorentz force they feel is in opposite direction, and hence they move in different direction. Okay, now we will come to the Hall effect. So this is the charge distribution you will have after some time for this rod. Okay, so here we have our Hall effect structure. So this is a box, or what you can say a small like flat surface, and having very small height but a good width. Okay, so okay, so this is our eye at the top, and the magnetic field is in upward direction. Okay, so this is a simple construction of Hall effect we all see. Now if you have eye view, you will see this setup like this. These are the wires, this is the battery, and the magnetic field are like this. So this is the eye view. Now at here, the same thing we have in this semiconductor. There are holes and there are electrons. Okay, and you know that in this case when we apply the battery, then the direction of motion of electrons and holes are opposite to each other. Yes, their drift velocity, which is v1, v2, may be different, but the basic thing is that the velocity of both of them are in opposite direction. Okay, and this implies that the force, the Lorentz force, both of them should have must be in same direction. How? Let's see. So this is the basic representation of holes and electrons. And see, here there is written Fh is the force on holes, F is the force on electrons. So you can see what we see. And also an important concept that we are doing v1 cross b, the angle between the velocity and magnetic field is 90 degree and sine 90 degree is 1. So I have not shown that, I have simply written f1 and f2, and see both of them are in same direction. Show you a animation which will help you understand that the force is in same direction for both holes and electrons. Okay, so see both electrons and fields Lorentz force in same direction at in this case. Now what's the concept is that the formula is F is equals to q v cross b. This is the Lorentz force. So if both holes and electrons have same velocity, which we have seen in the rod case, then the direction of velocity they will experience the force in different direction, and hence they will move opposite to each other. But if both electrons and holes have different velocity direction, which we see in the Hall effect case, then they will have Lorentz force in same direction, and so they move in same direction, as we can see in the Hall effect. So this is the basic thing. V and Q, they are the most important thing in this, which decides the direction of force. Now another important question, because what I have said is against what book teaches us, it's against what we have seen. So if I am going against your assumption, like I am not going any against, but if this is the case that both holes and electrons are moving in the same direction, then how will you have a Hall effect, sorry, how will you have the Hall voltage developed between this plate and this plate surface? Because in Hall effect we want that there is some maybe majority of electrons and then there is majority of holes, then there is net electric field established here. But if you say both electrons and holes move in the same direction, then then they will cancel each other effects, and there will be no charge developed here, no, and nearly no charge at here also. Like how will you get the Hall effect developed, Hall voltage developed here? So the answer to this question lies, I can answer this question in two ways. So first of all, I will answer for intrinsic semiconductors. So in case of intrinsic semiconductors, see, I have written V1, V2. V1 is the drift velocity of holes, and V2 is the drift velocity of electrons. See, it's a basic concept that the drift velocity of electrons is higher than the drift velocity of holes. That is, velocity V2 is greater than V1. So it implies that the force F2 will be greater than F1. Very simple. And so the electrons will move very fastly here as compared to the holes. And so the majority here will be of the electrons nearly. Yes, the case will be obviously that positive will come and diminish them, but it will happen a little slower as compared to this. It will happen a little faster because the velocity, the force F2 is greater than F1. Mathematically speaking, you can see over here you can read this. This is what I have said now. Okay, now the another answer of this question for extrinsic semiconductors. So in extrinsic semiconductors, see, in when we are talking about hall effect, we are mostly talking about either n type semiconductor or a p type semiconductor. So in this case, the our discussion, like you can see, like what I'm saying here, in n type we have electrons in majority and holes in minority. So in this case, the contribution of holes and disturbing the Hall effect can be neglected. What I am saying is that suppose there are 10 electrons and there is one hole, okay, then we can neglect the effect caused by this one person. Now there are 10 persons here going down and this one person fighting against the 10. We can neglect this fight, obviously. So this is how, like, a Hall effect has been explained for n type and p type. In n types, they are just neglecting the effect of this person, this whole person. And in p type, the holes are in majority, so at here we neglect the contribution of electrons. And so overall the concept of Hall effect is still safe. But now, not it's not the end. Just a brief question for you before going is that, can you answer like the thing, this case, like I'm going to ask the question for intrinsic semiconductor case, and you have to show the answer of my questions mathematically if possible. So the first question is that for the intrinsic semiconductors, the battle between the hole and electrons will end. So what do you think, will it end or not, or on what parameters it depend that the battle between the holes and electrons will end? Because see, they both are rival of each other, they will try to damage each other. So will the battle end? Or if suppose electrons wins the case, they are winning. So if electrons wins the case, that is there is a majority of electrons at this another side, then will the equilibrium be achieved in intrinsic semiconductor? Because see, what we see in Hall effect is that we say that after some time there will be a equilibrium, no net force in upward the net force in upward will be balanced by the net force in downward. So will the same equilibrium be achieved here? Because here we are finding a new case which says the rivals between electrons and holes. So for this, now I will end this video. Thank you guys.